It's all yours.
Okay, thank you gentlemen for giving me the opportunity to present to you about a couple of things. First of all, how air circulation and destratification improves thermal comfort and saves AC energy, and also about our products. My name is John Brodie. I'm the Managing Director of Airius Oceania, and just to give you a bit of background, Airius is a company that's based in Colorado in USA, and is a large plastics and mouldings manufacturing company, and as a privately owned company, been in operation for 52 years now. And Airius is a subsidiary of Avalon Engineering, and Avalon Engineering was probably the largest moulding company in America. And so they made all the moulds for the Ford car dashboards, they made moulds for telephone handsets, they made moulds for the JBL speaker cones, and numerous other products. Airius is an engineered Airius air pairs are an engineered air turbine. And what we specialise in is moving air over long distance in a narrow focused column using very low amounts of energy. So it's a patented air turbine, all designed, engineered and manufactured in-house by us, everything except the motors. So today I'm going to talk to you about how air circulation, which is what we do, circulate air, and destratification, which is what we do, will improve thermal comfort and save AC energy. And at the end of the presentation, I'm going to give you some information on our products and some of the applications you can see where it works. This is a science-based presentation. It's evidence-based, it's not something I've made up, and it's based upon all the studies and research that I've done in my studies. And it is, it entitles you to a 1 formal CPD point under the refuel system for the Australian Institute of Architects. So everyone, please make sure you fill out that form that's going around, because I need to have all your details so I can issue with the certificate. And I'll put you on our newsletter so you'll get our updated product information, because we're releasing new products all the time. So today, the learning outcomes are that at the end of the presentation, hopefully, if you're paying attention, and I'll make sure you're paying attention by asking you different questions, you'll be able to define thermal comfort and list physical and environmental requirements to achieve it. You'll be able to recognise the benefit of air circulation for cooling, comfort and building design. You should be able to explain destratification and its benefit for improving comfort in the heating environment. You should be able to discuss how destratification can save both heating and cooling energy in buildings. And you should be able to identify which building types benefit from the use of both air circulation and destratification. And finally, you'll get some idea about how directional airflow can be used to improve naturally ventilated building design. So if you've got any questions as I go through, feel free to ask me. But there's a lot of information that we're going to go through, so I hope I don't lose you. So, thermal comfort. Right, so sitting here now, who's comfortable? Put your hand up. Well, you're all comfortable. Okay, but you're wearing a jacket, you've got short sleeves on, you've got long sleeves on, you've got a jumper on, but you're all comfortable, but you're wearing totally different clothing generally. So that means that there's different heat levels being generated by the body. So what I'm getting at is that thermal comfort's very subjective and very individual. And as you'll see here, you're all sitting in a space that's the same temperature. The temperature's roughly 23 degrees in here. So it's 23 degrees, you're all comfortable, but if you took your jumper off, or if you took your jacket off, you might find you're not comfortable. So there's a difference based on what you're doing and what you're wearing, for a start. Thermal comfort is a condition of mind that expresses satisfaction with the thermal environment and is assessed by subjective evaluation. So it's a subjective thing. What you think's comfortable, what your wife thinks comfortable, are quite often very different things. For example, what your children think's comfortable, or your grandmother, or your mother, or whatever, there's big differences about what people find comfortable. So it's very, very subjective. And maintaining this standard of thermal comfort for occupants of buildings or other enclosures is one of the important goals of air conditioning engineers, but it should also be an important goal for architects. Guys like yourselves should be able to understand thermal comfort in a building so that I can improve the outcomes for my client. And my client needs to have a building that's secure and comfortable. That's why we build buildings. Now, the physics of thermal comfort are quite simple, based on this sort of data. So, thermal comfort research started in the 70s. It's quite flawed research. It's not not a very good research base, but it's been utilised and then adopted by air conditioning engineers and others to try and explain what comfort's about. And this is the most basic level of thermal comfort, and this is what your engineers use when they design a building from a thermal comfort perspective. There's 4 environmental parameters and there's 2 personal parameters. So the clothing insulation and the metabolic rate are personal parameters, so what you're wearing and what you're doing. And the environmental parameters are air temperature, which is exchanges between your body and the air, or convective exchanges. There's mean radiant temperature, which is temperature of the surfaces of the building generally, for want of a better term. And there's airspeed, which is what we all know, convective and latent exchanges. And then there's humidity, which is a latent exchange. Now, out of those 4 points there, the one that architects and designers have the most influence over in a building is airspeed. Because if you design your building, you can improve the airflow through that building through quite a few methodologies. One of them, of course, is fans. And fans, air movement, as you'll find out in this presentation, does have a significant impact on thermal comfort. And also the way that you design the building, the way that you change the pressure on the facades, the way you locate the windows, the way the windows open, the shape of the building, floor to ceiling temperature differences can equal different pressure differences and airflow in the building, so you can use natural buoyancy to ventilate the building. So as a designer, you can do a lot to improve thermal comfort simply through the use of airspeed and manipulating that airspeed.
Sorry guys.
You're right.
Are there any miscellaneous books or folders and things that...
Is that one there?
Oh.
That's mine.
Gary? And a little manual, fairly white coloured thing. Sorry.
Yeah.
Can't see it, but anyway. Okay.
If we find it, we'll let you know. Okay, so that's the basic physics of thermal comfort. There's 4 environmental parameters and there's 2 personal parameters. But as we've done more and more thermal comfort research over the last 30 years and we've gone to more and more sustainable building design, there's a whole lot of research now that sort of adds to that. For example, what makes you comfortable? What was your expectation? What were you brought up with? What was your psychological expectations? What were you, did you grow up in an air-conditioned house? Did you grow up in Cairns and now live in Hobart? Did you grow up in Hobart and now live in Cairns? There's quite a lot of physiology and psychology around thermal comfort. Was I just going for a run before someone asked me if I was comfortable on a really hot day? Have I just come out of the snowfields and I'm freezing cold, so I'm not comfortable? It depends on what you've been doing, what you're wearing, what your expectations are, what your conditioning is. Do you feel sick? There's all different ways that you can interpret and manipulate what's comfortable in a building. It's not just based on those 6 parameters there, but that's what the engineers use when they design a building around thermal comfort prerogatives. So as we get hot, as the body heats up through exercising or just being, just existing, you generate heat, and that heat has to be removed from the body or you'll end up overheating and you'll end up dying. And one of the key ways to remove heat from the body is through air movement, and it's called evaporative heat loss. So what happens is the body starts to overheat, you perspire, which has got what's called latent heat in the moisture. That moisture contains heat, so the faster you move that moisture off the skin, the cooler you'll feel and the faster you'll feel cooler. So, as I know you all go running every morning, you come home and you're all really sweaty or you're bicycling or something. If you're really, really hot and it's a really, really hot day and you're perspiring madly, if you stand in front of a fan, you will instantly feel significantly cooler. Like we're talking 10, 15 degrees cooler. If it's a 35 degree day or a 38 degree day and you're really, really perspiring, stand in front of a fan or get in front of a breeze, because the faster that moisture gets off your skin, the faster you'll feel cooler and more comfortable. So evaporative heat loss is a significant component of the energy balance in the body. And as we get hotter, as the temperature gets above 30 degrees, the primary way of removing heat from the body is through evaporation. Perspiration equals evaporation, and that's the best way to cool the body down. Now, as you're all sitting there relaxed, hopefully, you're generating around about 58 watts a square metre. That's called 1 MET. So that's like a term that we use for defining thermal comfort and heat levels. So you're sitting there generating 58 watts a square metre, but the human body is equivalent to 3 to 4 square metres of space area. So that means you're generating, just by sitting there, just from your skin, 200 odd watts just by sitting there. And if you start running around the room, so if one of you gets up and decides to go for a run around the room, you might get up to 300 or 400 watts. If you go running outside, when you get a bit of speed up, you'll get up to 550 watts per square metre. So you can see, when you start to get a lot of people in a room, you start to generate a lot of heat. And you've got to get rid of that heat if you want people to cool down. Now, if you've got an environment that you're building a house in or a building in, then you need to modify that environment to ensure that you provide thermal comfort. Now, our engineers, in their great wisdom, who designed for an air-conditioned building, try to design the building to sit into that little square there. So what they say to you is, oh, well, everybody likes it at 22.5 degrees centigrade and 300 lux. So we want to make sure that that's what we get in that building, in an air-conditioned building. The trouble is that most climates don't fit into that criteria for most of the year. There's quite a lot of climates don't get anywhere near that criteria. Like Moscow, for instance, never gets up there. Khartoum never gets there. New Delhi, bits of it might get there. In Singapore and London, bits of it might reach that for a month or two. But most climates don't stay in that temperature zone that's supposed to be ideal for thermal comfort for very long. So you have to modify the environment. You have to change the design of your building, in theory, so that you can improve the thermal comfort levels inside the building. And if you understand about thermal comfort, you'll understand what needs to be done to try and increase the levels of comfort inside that building. So as we've gone more and more into sustainable buildings and less energy use, the adoption of natural ventilation, the adoption of understanding thermal comfort has become more and more important and more prevalent. The research is becoming very, very strong that if you offer people more control over their environment, they will tolerate a greater range of temperature. So if you work in air-conditioned offices, you'll notice that not everyone's comfortable. So do you want to stop?
It's all happening. Yeah, if you're...
It's going on. We're all buzzing. We're all buzzing. Most of us are buzzing. So